In this chapter, we're going to use some of the language that we've learned and try and figure out how to speak with it a little bit. So we've learned the letters of chemistry, we've learned how to make some words in chemistry, we know the symbols for the atoms, we know the formulas for different chemicals, different molecules. In this chapter, we're going to use that language and perform some calculations and look at chemical reactions, look at some of the sentences, try and do some determinations using that. There are lots and lots and lots of units in our society and in science. The next unit is just another unit, and it's called mole. It starts out like molecule, but it's not. It's its own unique unit, and it's called mole. It's analogous to dozen. If I said I had a dozen of something, how many would I have? And it doesn't matter what I'm talking about, but if I have a dozen molecules, well, that means I have 12 molecules. A dozen always means you have 12 of whatever that is. A mole means you have an incredibly large number of something. If you have a mole of something, you have this 6 number times 10 to the 23rd of that. If I had that many molecules of water, I would have gram quantity of water. If I had just one water molecule, it's a tiny, tiny mass amount. But that number, that huge number, I would have gram quantity. If I had that quantity of ping pong balls, that volume would be about the size of the Earth. This mole quantity is also referred to as Avogadro's number. And this number you can program in your calculator. It's also given to you in your information packet. When we use this number, you can use all those digits, the 6.0221367 times 10 to the 23rd. Often, I only take 4 digits, 4 significant figures from it in my calculations. Use at least 4, 3 or 4, and you'll be okay in most of your calculations. So if I was going to say I had a mole of whatever, but in this case helium atoms, it means that I have 6.022 times 10 to the 23rd helium atoms. If I had a mole of glucose molecules, I have the same number. C6H12O6 molecules. If I had a mole of this ionic compound, this calcium phosphate compound, it doesn't matter what we're talking about, it's the same number. It's a number to number relationship. And we're putting units here. If you wanted to use the word compound, calcium phosphate compounds, that would be okay too. But a mole is a number unit. Just like atoms, number of atoms is a number unit. This would be like saying I have 12 dozen cookies. That means I have 144 cookies. It's a number to number relationship. Note on this slide you can also make some other relationships. You just may not realize it quite yet. But if I had one calcium phosphate compound, and we'll just write the word unit, or you could write the word compound. You could look at that compound and say how many calcium 2 plus cations are present. You could also say, per unit, how many anions are present, how many phosphate 3 negative ions are present. Look at the compound, pause the video, look at this compound, and fill in these numbers. So pause the video, unpause when you plug in the numbers. If you look at the ratio, there's 3 cations per 2 anions in the formula. There's 3 calcium ions per unit, and remember this phosphate, that PO4 is 1 anion, and there's 2 of them. Okay, let's do a little bit of going from one unit to another with some of the relationships that we know about. What if we had 1 mole of helium atoms? What if we had Avogadro's number of helium atoms? What would be the mass? And I want you to go all the way to grams, so G, of helium. Okay, how would we do this? Well, we got to go from a number unit atoms. So maybe we have atoms we're starting with. Somehow we got to get into a mass unit. We know we can use the periodic table to say if we had one helium atom, what's its mass, but that relationship is between one atom and AMU. So if you could get that, that could be the next step. Go from atoms to AMU. So that's the mass, average mass of one helium atom. In the information packet, once you have that AMU mass, there's a relationship between AMU and grams. So this is going to be a two-step process. So 2 conversion factors. Go ahead and pause the video and get a number for us. Unpause when you have your calculation. And when you're done, since we started out with 4 significant figures in the number of atoms, go ahead and round your final answer to 4 significant figures. The average mass of one helium atom is around 4 AMU, and that's what we're using in our first conversion factor. And, just canceling, helium atoms and helium atoms cancel, and that would give us a mass, but the unit is AMU. The next step is to write down the relationship between AMU and grams, which is given in your information packet. If you had 1 AMU, it's a tiny, tiny, tiny mass in grams. And we have that conversion put in there, and as we go through, cancel out the units. AMU and AMU cancels, and we're left with grams. Our number is 4.00, well, that's kind of strange, 281.2259 grams. Rounding that to 4 significant figures, so a little equal in a squiggly line, it's approximately 4.003. We're rounding at that 2 position to thousandths. It's greater than 5. The digit next to the right of the 2 is greater than 5, so 4.003 grams. Oh, that's kind of strange. That's the exact same number as that number, but it's a different unit. There's a special relationship about that we're going to talk about on the next page. And it comes based upon the definitions of the mole and AMU. There's a special definition between grams, moles, and the periodic table. And this arises because of other definitions. And if you have pure carbon-12, so that particular isotope, the mole quantity is defined, that number is based upon having exactly 12 grams of carbon-12. And if you remember when we talked about AMU, the definition of AMU, carbon-12 is defined to be exactly 12 AMU. Because of this, we're going to be coming up with a definition on this page. A definition that relates mole quantity, gram quantity, and atom quantity. And in the end, you'll just have to memorize it, and you'll just have to believe it. It's like we believe that there's 454 grams in a pound. We'll just believe that this relationship is true too. From this relationship, so carbon-12, if I had 1 mole of carbon-12 and I had exactly 12 grams of carbon-12, how many carbon-12 atoms do we have? And this number is actually experimentally determined. It was theoretically predicted when Avogadro first looked at it, but now that number that we're giving you, it's an experimental number. You measure out exactly 12 grams and use a device like a mass spectrometer to get how many atoms are there. And just keeping 4 significant figures, it's 6.022 times 10 to the 23rd. Because AMU in its definition is based upon carbon-12 and the mass of carbon-12 is exactly 12 AMU, we're going to come up with this next relationship. But if I had 1 helium atom, like we said on the previous page, so 1 helium atom is exactly 4.003 AMU. Well, if I had 1 mole of helium, so a huge number of helium atoms. So this means I have 6.022 times 10 to the 23rd helium atoms. So a huge number. What's its mass? Well, the relationship we get is it's this same number that you get from the periodic table. And we'll just accept it. We'll just believe it. So it's 4, but instead of being an AMU unit, it's a gram unit. So it means we have this mass, this gram unit of helium atoms. So 1 helium atom is 4.003 AMU, which is tiny. If I have 1 mole quantity, it's the same number, but gram. So 1 mole of helium is 4.003 grams. This is true if I had a molecule or a compound. If I had 1 H2O molecule, what's its mass? Well, we got it to be about 18.01 AMU. That's if you had 1 molecule. If I had 1 mole of H2O, so I have a huge number of H2O molecules, the number that goes here with grams of H2O, it's the same number. It's that same 18 number. And we'll just have to believe that it's true. Just like we believe the relationship between meters and yards. They're all based upon definitions. But if we look at this relationship we just established, you can do this for any chemical. And it's a number, mole, to number, molecules or atoms, to mass unit. We can make this 3-unit relationship for any chemical. It'd be no different than having a relationship between yards, feet, and inches. But in this case, we have a relationship between moles, and if we, could be atoms, could be units, could be molecules, but we'll just write the word molecules. Moles, molecules, and grams. There would be numbers that go in front of each unit. Moles and molecules, they both start out being spelled the same way. They're different. And the numbers that go in front of them are different. When you make this 3-unit relationship, you'll just have to memorize this, but what numbers go in front of each unit? Always put a 1 in front of mole. It's kind of like when we taught you to do metric prefixes, put a 1 in front of the unit that has the metric prefix. The 1 goes in front of mole. In front of molecules, it's always Avogadro's number. So 6.022 times 10 to the 23rd. That would go in front of molecules. If we're talking about a molecule, it would go in front of atoms. If we're talking about atoms, it would go in front of unit if we're talking about an ionic compound. What's different from chemical to chemical is what number goes in front of grams. And it depends upon what chemical we're talking about. To get that number, use the periodic table, see the masses of each atom that's part of the chemical, add them together, and you get that number. But if we're dealing with mole quantity, then it's a gram unit. If we're dealing with 1 molecule, then it's an AMU unit. Practice. You'll get it down. You'll be able to speak this language beautifully. The mass of 1 mole of a chemical has a special name. It's called molar mass. It's the mass of 1 mole. And you can look at the chemical, and using the periodic table, you can get the mass of 1 mole of that particular chemical. Doesn't matter if it's an atom, doesn't matter if it's a molecule, doesn't matter if it's an ionic compound. So we could do it for copper. If I had 1 mole of copper, so a huge number of copper atoms, how many grams of copper would that be? So I need to go to my periodic table, find copper, look at that number, and we see that 63.546 number. If I had one copper atom, it'd be 63.546 AMU. But if I have a huge number of copper atoms, if I have 1 mole of copper atoms, then it means I have 63.546 grams of copper. Okay, let's go ahead and pause the video, and I want you to figure out what's the mass of 1 mole of O2. So how many grams of O2 would that be? And what if I had 1 mole of an ionic compound, sodium chloride? What would that mass be of sodium chloride units? So go ahead and pause the video. Unpause when you're ready. When we look at oxygen, just remember that there's a 2 there, so it's not just that 15 number. It's that 15.99 number. Add it twice, so it's approximately 32. 31.9988 grams. If I had 1 mole of oxygen molecules, O2, it'd be around 32 grams. If I had the same number of copper atoms, so same number, it'd be more massive. It'd be like if I had 10 small cookies and 10 big bagels. Each bagel had a larger mass. Same number, but it'd have a larger mass. Okay, for sodium chloride, you need to add the numbers for sodium and chlorine. For both of those, when you add them together, you get around 58. A little more, 58.443. So look at the decimal number for sodium and chlorine and add them together. This is called the molar mass. And just a couple notes about molar mass. Sometimes in some of the problems it may just say the molar mass of this compound is, and it may be written like this. Instead of as a relationship, we could say the molar mass of O2. Well, there's 31.9988 grams of O2 per 1 mole of O2. The units are grams per mole. Okay, so that's molar mass. Note, we talked about molecular weight and formula weight. The molecular weight is the mass of one molecule. And so it's still the same number for oxygen. So if this was for O2, it'd be 31.9988. But instead of grams, because it's only one O2 molecule, it would be AMU. Formula weight and molecular weight, often and usually the units are AMU. And they may not be given to you in the problem, but it's AMU. Molar mass is grams per mole. And one last note for this slide. If you have the molar mass, 1 mole of something, again, you have exactly the same number. And we could tag Avogadro's number, which I did magically and quickly, to each of those relationships that are up there. You have exactly the same number. And this gives us a 3-unit relationship for the different chemicals. For copper, it's mole to grams to atoms. For oxygen, which is a molecule, the one we have here is moles to grams to molecules of O2. And for an ionic compound, it would be moles to grams to formula units, or just units, of sodium chloride. So we have a new relationships, and it's no fun to have a relationship without going out and doing something. So we're going to use these relationships to convert between units. And our relationship, it's between mole, grams, and the number of that particular chemical. In this problem that we see below, we have helium. So go ahead and pause the video and write the 3-unit relationship for helium. How many moles of helium, how many grams, and how many atoms. We've done it before, but we'll go ahead and rewrite it. So pause the video and then unpause. So here's our 3-unit relationship, and we're going to use 2 out of those 3 to make a conversion factor. As we look in the problem, what are we given? We're given a quantity, a mole quantity, and we're supposed to convert that into grams. It's the same amount of helium, just a different unit. As we begin the problem, we have 1.85 moles of helium, and we need a conversion factor, and we're going to grams of helium. If we look at the relationship, what does the relationship tell us? If we had 1 mole of helium, its mass would be 4 grams. If I had 4 grams, it means I have 1 mole. If I have greater than 1 mole of helium, 1.85 moles of helium, I should have more than 4 grams of helium. Make sure your answer makes sense. So go ahead and pause the video, make your conversion factor from that relationship, get an answer, and unpause and check your answer. This particular problem just required 1 conversion factor, but as we look at it, moles and moles cancels, and we're left with grams. We start with 3 significant figures, so keep at least 3 in your final answer. If I need exactly the correct amount of significant figures, I would tell you that in the problem. But the answer is approximately 7.41 grams. On this page are a few more example problems using the relationships between moles, grams, and Avogadro's number. The first problem is for sodium chloride. The molar mass, the 3-unit relationship for sodium chloride, we did that a few slides before. You should be able to get that, but you already have it. You need to go from grams to moles. Go ahead and pause the video and set up this problem. Check your answer when you're finished. The molar mass gives a relationship between grams and moles. So if you're going between those 2 units, it's a 1-step conversion factor. So going from grams to moles or moles to grams, you'd use the molar mass of that particular chemical. The molar mass of sodium chloride, 1 mole of sodium chloride, the molar mass, it's always the mass of 1 mole, is approximately 58 grams, 58.443 grams. So if I have 117 grams, I have more than 1 mole of sodium chloride. 1 mole of sodium chloride is 58.443 grams. Always make sure your answer makes sense. But grams and grams cancels, and we're left with answer, which is approximately 2.002 moles. The next problem. What if you had 36 grams of oxygen? We know the molar mass of oxygen, and we know how many oxygen molecules there are in 1 mole. We have Avogadro's number. The molar mass of oxygen is around 32. You have 6.022 times 10 to the 23rd molecules of O2 per 1 mole, or per approximately 32 grams of oxygen. If we have 36 grams of oxygen, we should have more than Avogadro's number of molecules. Make sure your answer makes sense. And don't confuse moles and molecules. They're 2 different units. So go ahead and start with this 36 gram quantity and figure out how many molecules of O2 are present. So pause the video, give it a try. The 3-unit relationship for O2 tells us if we had 1 mole of oxygen, there's approximately 32 grams, 31.9988 grams. If you have 1 mole, you have Avogadro's number of molecules, 6.022 times 10 to the 23rd. That many molecules per 32 grams for oxygen. So if we cancel, grams and grams cancels, and your math, and get your calculation, it's approximately 6.77 times 10 to the 23rd. A larger number than Avogadro, so the answer seems to make sense.